Leetcode problem, largest component size by common factors. So the problem is that we are giving an integer array of unique positive integer nums. So for example, for 6, 15, and 35, so we're going to consider the following graph. So there are nums lengths not labeled from nums 0 to nums n-1. So this is the length. Yeah. So there is a undirected edge between nums I and nums j if nums I and nums j share a common factor greater than 1. So for example, 4 and 6, they share a common factor 2. 2 is greater than 1, so 4 and 6 are connected. And also for the number 6 and 15, because they share a common factor, for example, 3. Yeah, and for 15 and 35, they share a common factor because 15 is going to have a common factor 5. So this means all those nodes are connected, and we're going to check the longest connected components, basically. Yeah. So let's first check what is the values of this nums I. It's going to be more than and equal to 1, less than and equal to 10 to the power 5. So this means while we are using the unified, our node is starting from 1, not 0. Yeah, so this is one thing. Another thing is how can we use the unified to solve the problem? So for example, if we have a number of 4 and 6, how can we check that 4 and 6 are connected? We know that they have a common factor, but how can we find the common factor for this number 4 and 6? So we're going to use the unified to check. So for this number 4, we're going to have the prime factors with 2. And for 6, we're going to have the prime factors with 2 and 3. So if it is like this, basically we're going to connect the component. So for example, this is a 6, we have 2 and 3. Because 2 and 3 are common factors, so this means 2 and 3 are going to be connected. Because basically, no matter if it is a 2 or 3, it will represent this number 6. And for this number 4, so 2 will represent this number 4. Because 2 and 3 are connected, basically this 2 and 3 are connected. This means number 4 and 6 are connected. Let's just use another example. So for the number 15, it has the prime factor with 3 and 5. Yeah, because 3 and 5 are more than 1. So this means 3 and 5, we're going to connect 3, 5, because this whole part, 3 and 5, we're going to check this whole part as this number 15. No matter from which place, if we find a 3 or 5, definitely that number going to connect to 15. But for this number 6, we have a common prime factor 2 and 3. And here we also have a 3. Yeah. So this means 3 and 3 are definitely connected because it is itself while we are using the unified. So this means 2 and 5 are going to be connected. Yeah. So basically this number 6 and 15 are going to be connected because all those sub-components connected. It means our component with 6 and 15 are connected. So this means 4 and 6 are connected, 6 and 15 connected, and also for this number 35. Yeah. So there are going to be two steps. The first step is that we're going to use the unified. We're going to use the unified to check the connected component. And secondly, we're going to check the prime factors. We're going to use the prime factors to check each number. So for example, for this number 15, we're going to have the prime factors like 3 and 5. And for this 35, we have the prime factors as 5 and 7. So if they have the common prime factors, means this is 5 and 5. So this means this is 3, 5, this 5 and 7 connected. This means the number 15 and 35 are connected. Yeah, so this is how can we solve the problem. Normally inside the unified, it is not this number itself. It is all the prime factors. We're going to put all the prime factors inside the unified. If we put it inside, definitely, if this is a common 5 with this 5, it means the number 15 and 35 are connected. Yeah. And finally, we just check the largest connected component for unified. Definitely, it's going to be easy. Yeah. So for this problem, I'm going to copy some template code because basically this is a template. You don't need to think about it. Yeah, I mean from anywhere you can just use it. Yeah. So for the unified, if you write a lot of unified, basically you should have this kind of unified template. But for my template, my index is just starting from 0 to n minus 1. This means my node is 0 to n minus 1. But for our problem, it is 1 to n. So definitely I need to starting from 1 for the unified. So another template, it is the divisors. So it is the prime factors basically. So this means if we are giving a number, for example 15, definitely we need to have this 3 and 5 as the prime factors because we need to check the common prime factors. Yeah. But before that, let me just give a random return as 0, and let's just check what is inside the divisors. So you're gonna understand why we're gonna do it like that. So this divisor method is did by the acytosis save. So for acytosis save, it can be used to check the prime numbers, but we can use the same code, but just to change a little bit from here. Yeah, because for the acytosis prime numbers save, it's gonna be I times I, but for our check, it only be prime factors. So here gonna be starting from this I. Yeah. Now let me just check what is inside the divisors. So this is helpful for us to understand how can we solve the problem. Yeah, but while running the code, maybe I'm gonna just start to do some preparations for the unified. I'm gonna set a UF. So it's gonna be the unified. It is the maximum of the numbers plus 1 because my node gonna be starting from 1 to n. Yeah, so this is why I use the maximum of the numbers plus 1. So I just want to keep the unified big enough. Yeah, now I want to check all the numbers. So for n inside the nums, and I want to check all the prime factors. So in Python we can use pairwise. Yeah. So pairwise is just to pairwise two numbers. For example, if we have number 1, 2, 3, it's going to be pairwise like 1, 2, and 2, 3 because we can check it directly. Normally for unified, we can use this kind of method. So for A being pairwise with the divisors with this number, so we check out all the divisors and we're going to pairwise them and we're going to put it inside the unified. So uf.union with this number, I mean the prime factors A and B. So currently we prepared the unified. Now we just need to check the final result. So the result I think the network problem, but I will try to run it later. Yeah, let me first finish the definition of the dictionary. So I'm gonna prepare a default dict, and it will be the integer as the value. Now I'm going to check all the numbers inside the nums. Yeah, but I want to check if two components are connected. So basically, I need to check the prime factors, not the number itself, because I didn't put the number inside. I just put the prime factors inside the unified. So I needed to use the uf.find and divisors n. I need to find any random number. I mean any divisors is okay. Yeah, let me just choose the first divisors inside 0. You can also choose -1. I mean any index inside it should be okay. So as they are connected, I just need to find their parent and +1. And in this way I can get the maximum value. So the final result is gonna be d dot maximum of d dot values. Yeah. Now let me run it to check if everything is okay. At the same time, we're gonna check what is inside the divisors. Maybe I'll just copy the link and try to run it in some other places. Maybe it is faster. If it didn't work, Yeah, I think I had the network problems. Normally I should not try to record it. Yeah, but let's just have a try. It didn't work. Yeah, and why this method works? Because for unified, basically we can analyze the time complexity as O1 or log n time. It is also okay. This is for unified. And for the divisors for each of the number, we can use log n time to analyze. Even the number is really big, we can still use yeah, because here for the time complexity from here, basically this is n log n time. So our number n is 10 to the power 5. So this means it should be okay. Yeah, but this is just runs in one time, and after that we will not run it. We just use the divisors dictionary. Yeah. So we're going to focus on analyzing the time complexity from here. So this is O(n) definitely. And for here, as I said before, we're going to use the log n time to analyze, because basically for finding all the divisors, this is going to be log n time. And here we're going to analyze as O1, or you can analyze it as log n time. So it's going to be log n squared times n. So n times the log n squared is going to be the final time complexity. I think I would to have a refresh to check if I can submit it. Yeah, because I just need to get the testing case passed to prove that the code should be okay. If it is not okay, let's just yeah, I think it didn't work. Maybe I gonna try to submit it in another place. Maybe yeah, the US website should be okay. Yeah, because basically from China, the networking from here is really bad. Let me try to check this question from the another place. Maybe from here. Yeah, let me just check this question 952. Yeah, let me just use the same code to check if it works. Maybe next time I should use the US website, the .us website. Maybe it is better. Yeah. Now let me just run it to check. I think I copied something wrong. Let me just delete these areas. I hope they used the same variable and same class name. Yeah, let me just run it. Yeah, as you can see, it's accepted. Yeah, now let me submit it to check if it can pass for all testing cases. Here is something wrong. Index goes out of the range. Let me have a check. Let's execute the input. This means my uf.file is wrong. It should be my number divisors n with 0. For inside the pairwise divisors n. Yeah, I didn't run it from here. Yeah, let me just check the same code. Yeah, I think I need to check this number n if n, because n cannot be equal to, yeah, because in this testing case there's this number 1. Yeah, because normally this number cannot be 1. Yeah, I needed to check this number n. So if n not equal to 1, we're gonna put it inside. Yeah, let me just recheck. Yeah, it works. Yeah, because this number, we're gonna check all the connected component, and all the prime factors should be just 2 like 3, but it cannot be 1. Yeah, so if this n equal to 1, basically we cannot find it, because divisors 1, 0, because there's nothing inside. Let me just print out the divisors. Now we can check these divisors. Yeah. Let's check what is inside of the divisors. Because while we are preparing these divisors, basically there's no 1. As you can see, it's just starting from 2. So this is for checking the prime factors. Yeah, because for number 1 we don't have prime factors, so that is okay. Yeah, so while we are checking the numbers, so if it is equal to 1, we just ignore it. So the numbers should not equal to 1, as in this example. Yeah, if it is 1, one cannot connect all other numbers because they don't have the common prime factors, definitely. But for all other numbers, we're gonna check it. Yeah, and also, because my divisors, I didn't prepare 1, because I always prepare the prime factors, so I didn't prepare 1. So I have to check if this n not equal to 1, and then I'm gonna use the uf.find and to check the connected component, and then I'm gonna return the maximum connected component. So it also means the longest connected component. Yeah, let me just submit it to check if it can pass for all testing cases. Yeah, now as you can see, it works and it's pretty fast. Thank you for watching. See you next time.